right, greetings YouTube, beautiful mind here. This will serve as the lecture for. We are in week 4, Wednesday for Calculus 1. I hope everyone is doing well amidst all of this COVID stuff. It's a very interesting time to be alive. Hope everyone is doing well. I feel good. I feel like I'm in my rhythm and flow. I totally am enjoying not having to drive an hour one way to come into work every day. For the longest, I always felt like I was like, dude, well, what are we coming in here for? It's like it's the same information, and I get the whole thing about having presence, but people don't really appreciate it. Like they do, but they don't. I don't know. It's kind of strange. Um, but I totally appreciate not having to leave to like do the same presentation, and then but I'm still available. Like nobody really uses my office hours like that, so I don't. I'm like, why am I driving here for convenience and to make people comfortable? But they don't really take advantage of it. So that's neither here nor there. This presentation is pretty much the same way I would do it if we were in person. There are a few drawbacks though, like where we don't get the live tete-a-tete or the live back and forth, so that it is a drawback. I know we could use something like Zoom, but then it seems like everybody's not on that level, and it just kind of makes things a little bit difficult. So to me, this is just how it's coming out for me right now as far as the presentation, doing this distance learning. But I'm excited about it because this is actually half of like my ultimate goal. My ultimate goal is to be someplace tropical, still doing the same presentations, earning more money, being on like an island or something like that. Like I know people that live on islands, like they have their own island. Um, and it seems like it's feasible. So like it seems like it's not that impossible or whatever. Um, Impossible means I'm possible, or impossible. Anyway, something like that. But that's neither here nor there. But yeah, so ultimately, I would like to still be doing like similar presentations, making more money, and being someplace tropical. So that way, when I'm done, I just shut down my equipment and I'm on the beach or wherever it is that I want to be. So that's neither here nor there. For this week, the major announcements that we need to be aware of, we have exam 2 that is available on Pearson. Okay, so I went on and loaded it. I wanted to give you a little bit of time to make your way through it. It is due this Saturday by 11:59 p.m. We get unlimited attempts for the entire quarter, actually, but past the deadline, there's a late penalty of 21%. So the highest you can earn is a 79% past the late period. Prior to the deadline, you can get whatever score you want, essentially. So the first thing, again, is that exam 2 is available on Pearson. The other major announcement that we need to be aware of is we need to be sure to do the participation and verification quiz. Sorry, participation and honesty quiz on Moodle. Okay, so those are the main 2 things. Exam 2 on Pearson and a participation quiz on Moodle. Okay. As you kind of go through this material, write your questions down, and you have to reach out to me. If you don't ask any questions, I can't answer questions that you aren't asking. And a lot of times, if we don't like our experiences or the results that we're getting, more than likely we aren't asking the right questions. You can lead a horse to water, but you can't make him drink, right? But it's the teacher's job to make him thirsty. At least that's how one of my mentors put it. So that's neither here nor there. Let's take some time. Today, what we like to do, like to go through section 3.7 with the chain rule. Okay, so we're going to continue our discussion that we've been having on derivatives. So we've been using like these rules for differentiation. Once you catch the hang of them, they go fairly quickly, and I actually enjoy derivatives. So I hope that you are finding your passion in them as well. I will also be aware that we have tutors. Like we have tutors to help with all of these courses. They're they know what they're talking about. These are good people. And they're just sitting there waiting. So if you reach out, we have contact info in the announcements. If you can't find it there, if you reach out to me, I can connect you with them. I'm also open to going live for tutoring, but again, students are typically intimidated by my energy, so I stopped trying to. I just let that be, and anybody that wants to take advantage is more than welcome, and I just make sure to do my job and keep it moving. But we have tutors that all they do is sit and wait to answer questions. Okay, so again, I know my energy can be a little intense, so we have options. Also, this is another reason why I use Pearson. With Pearson, there's an explanation for nearly every question that we're doing in the homework, right? So the explanation is right there attached to each question. Inherent in each question is a solution, all right? Inherent in each question is a seed of its resolve, or something like that. Anyway, so bringing it on back, let's take some time to. I just want to do section 3.7, the chain rule, for today, and that'll be more than enough. I'll be monitoring my email and things of that nature. So during, just throughout the day, just to kind of respond to inquiries and answer questions and things of that nature. So chain rule formulas. To me, the simple way to do chain rule, I usually do the derivative of the outside function times the derivative of the inside function. That's the long and short for the chain rule for me, right? Okay, that's all I'm going to do. The derivative of the outside function times the derivative of the inside function. Okay, that's all that this is saying. Okay, so I'm just looking for the first example. Yeah, these are how to do the chain rule, but I'm just going to work this example. So let me get some graph paper. I really like my lines. It helps me. So find the derivative of the following functions. Let me add a page right here. Okay. I'm totally loving this presentation mode, by the way. So you can't see all the little things we're doing on the side, so it's a much better presentation. So let's take a look at example 1a to begin with. We have y equals 5x plus 4 to the power of 3/2, right? So if we want to find dy by dx, so the derivative of the outside function is going to be first the power rule, the exponent comes down, so we have 3/2. This just stays the same, 5x plus 4. And then if we say 1 minus that exponent, that becomes a half. So that's the derivative of the outside function times the derivative of the inside function. The derivative of 5x plus 4 is just 5. Okay. So we did like the power rule, and we did the derivative of like a linear function, right? Okay. I don't really see much more here. So then this is going to be equal to 15 over 2 times the square root of 5x plus 4. It's about the best we could do there. Nope. Undo. Let's try that again. Nope. One more time. Just trying to get my rectangle to activate. There we go. Like that and like that. Style. This about there. Okay. And you know what? Just for the sake of simplicity, let me shrink this down to one page. Okay. So again, for the chain rule, we did the derivative of the outside function times the derivative of the inside function. Okay. So we ended up with 15 over 2 times the square root of 5x plus 4. 15 over 2 times the square root of 5x plus 4. You see it there. Oh, I forgot the other ones. Okay. The root. Let's go ahead and do the others. So the second one was we have, so for example 1b, I think let me just be consistent since we are going to use these other pages. There it is. Okay. So for example 1b, we have y equals sine cubed of x. Y equals sine cubed of x. Okay. So then if we want to find the derivative of y with respect to x, so the derivative of the outside function is just going to be 3 sine squared x times the derivative of the inside function. Derivative of sine is what? Cosine of x. Okay. I can't see anything else there, so I think that's it there. Awesome. Style, I like this. Okay. I'm gonna go ahead and check that result. Mm-hmm. Let's say sine squared. Yeah, okay. And then let's go ahead and do example 1C. So C, what? Sine cubed. Oh, okay, sine of x cubed. Okay, I was like, why do they look the same? Y equals sine of x cubed, right? So in this one, if we want to do the derivative of y with respect to x, the outside function in this case is sine. So the derivative of sine is cosine of x cubed times, let me make that 3 look a little bit better. The derivative of the inside function is x cubed, so that's the derivative of that is going to be 3x squared. So I'm going to write the final answer as 3x squared times the cosine of x cubed. All right, this is what's going on. Okay, hopefully you were able to catch those changes. Again, all we were really doing was a derivative of the outside function times the derivative of the inside function. Okay. I'm not gonna worry about that right now. All right. 3x squared cosine of x cubed. And we see it 3x squared cosine. Okay, cool. Let's look at this example 2. Use equation 2 of the chain rule to calculate the derivatives. Okay, so we're asked to calculate these derivatives. So we have example 2a. The original function. Let me see something. I just want to see something with the notation. dy. Okay, d by dx. Okay. So the first one we have is 6x cubed plus 3x plus 1 to the power of 10. So we want the derivative of that function with respect. We want the derivative with respect to x of that same function, 6x cubed plus 3x plus 1 to the power of 10. Right? Let me add a page. Okay. So then the derivative of the outside function, the 10 comes down. This stays the same for right now. And 10 minus 1 becomes a 9 times the derivative of the inside function. 6 times 3 is 18. That's going to be x squared plus 3. And the derivative of a constant is 0. To take it a little step further, if we distribute the 10 into the far right, that's going to become 180 x squared plus 30 times 6x cubed plus 3x plus 1 to the power of 9. And that's about the best that we can do. So a few weeks ago, I found myself binging the movie Frozen 2, and in the opening scenes, there's the townspeople. There's a commotion, and the townspeople have to escape the city into the like nearby plains or plateaus or mountains or whatever. And so the little snowman Olaf is playing with the children, and they're like sticking icicles all in his face. And he was like, "We like to." He said, "We like to call this controlling what you can when you feel out of control." So I don't know. For some reason, that quote just went across my mind because all the how everything is kind of very chaotic right now, and a lot of people feel out of control. So I like that idea of controlling what you can when things feel out of control, and that's just to keep your mind clear and keep a level-headed. A lot of the safety and protection comes from just keeping a clear mind and being level-headed. Once you kind of panic, like when you're swimming, if you panic, that's when it just goes to the left. But as long as you stay calm, you can kind of position yourself and be in the right place at the right time, kind of deal. Water is so delicious. Oh my goodness. I love delicious water. I know that sounds very not normal because water being delicious, water is supposed to be bland and have no taste, but water definitely be having different tastes. Like depending on your source, you could taste metal and all these other impurities. And so like I have like this is alkaline water, like pH 10. It's a noticeable difference in texture, a lack of minerals. I don't know. It's just when you can drink the water and it's just like it just feels right in your soul. It feels so good. So anyway, that was 2A. Let me just check that answer before I go forward. So then 2A. Okay, 30, 180, right? Yeah, I think we got the same thing. I just distributed the 30. They kept the 30 separate. That's fine. So then 2B, we have the square root of 5x squared plus 1. To be or not to be. Example 2B, we have the square root of 5x squared plus 1. We're asked to find the derivative with respect to x of that function. Okay. So the derivative, so we're using the chain rule here. The derivative of the outside function, so the square root is the same as to the power of a half. So we're going to bring that half down. This stays as is. And a half minus 1 becomes a negative 1/2. Times, let me just drop down. I need some more space. Let me drop down to the second line. Times the derivative of the inside function is going to be 10x. All right. So then ultimately we'll get, that becomes 5x. So we have the square root of 5x squared plus 1 under 5x. Okay, I'm going to leave it like this. I think this is how the text. We usually don't leave radicals in the denominator, but I noticed that with stuff like this, it's just been leaving it. Keep in mind with our assignments, we get unlimited attempts at them, okay, prior to the due date, prior to the deadline. So 2B, let's see, how do we do? Right there it is, okay. 5x squared or 5x squared plus 1, okay. Let's go ahead and do one more, which is C. E to the negative 3x. E to the negative 3x. This is example 2C. 2C. Okay. So we're asked to find d by dx of e to the negative 3x. And that's going to be equal to, so the derivative of the outside function, the derivative of e is just itself. So it's going to be e to the negative 3x times the inside function. The derivative of negative 3x is just negative 3. Ouch, need to cut my nails. And I'm totally like gripping too hard. So then we can just write it as negative 3e to the negative 3x. So all we're doing is the derivative of the outside function times the derivative of the inside function. Style, we want to go here. All right, so that's 2C. I think that's it for that one. Am I missing something? Oh, I did skip something. I see. I just did 2D. Okay, so I'm gonna go back and do 2C. If that's 2D, let me add another page and let me go ahead and do 2C. So 2C, so we got 5t squared, 3t squared plus 2 under and cubed. Let me cut this guy. Cut. And this is example 2C. And let's paste. Okay. So we're asked to find d by dx of this. Okay. And that's going to be equal to, now the derivative of the outside function is going to be 3 times that function. So, but instead of finishing with the 3, it's going to finish as squared. Times the derivative of the inside function. So if we're going to do the inside function, it's basically the quotient rule. So it's low d high minus high d low over low low. So the low is this guy. Low d high So the derivative of the top is going to be 10t minus high, which is, run out of space, 5t squared. Times the derivative of the bottom is going to finish as 6t over the bottom squared, 3t squared plus 2 squared. Okay, I'm going to shrink this down to one line and put it in the proper form. So this needs to go here. I'm gonna get rid of this for right now. This goes like this. Let's undo, undo. Let's go like this. Nope. Let's go like this. That's fine. Okay. And then let's put this here. And let's move it up just a little bit. And bring it back up to size. Okay. Okay, so we said low d high minus high d low over low squared. Okay, so we said the derivative of the outside function times the derivative of the inside function. Okay. Let's see if we can get some cancellations or anything of that nature going on. Can we get anything to cancel? Let's see. There's a lot going on in this one. I'm not seeing any cancellations, so what I'm going to do is the following. This is going to be this. This is going to be the same as. So we're going to have a 3. I'm going to say 25t to the 4 times all of that stuff over there. I think I'm going to just leave all that spread out. I mean, we could expand it. I'm going to see how they do it. 3. I'm just going to copy and paste it right now also because I just don't feel like writing all that. Copy, paste. Okay. So we're saying multiplying by all of that. Then we're going to say all of that divided by. So if that square and that square, we're going to finish with a power of 4. 3t squared plus 2 power 4. We could expand this and get it into like one term. I just don't feel like doing that. Let me see what they did. If I see that they did it, I'll do it. Let's see. Blah, 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 blah. Okay, let's keep going. Let's keep going because I think they went further, right? Let's combine like terms inside the set of parentheses. 3, 25t to the 4. So then that's going to become, if we distribute this 10 here, okay, we're going to get 30t cubed 20t minus 30t cubed, okay, 3t squared plus 2 to the power of 4. Notice that this cancels this. Okay, let's keep going. And I need some more paper. So then 20 times 3 is 60. 6 times 25 is 150, so 1500, right? So that top becomes 1500 t to the 5th, and the bottom is 3t squared plus 2 to the power of 4. Let me get this to fit onto this page. All right, I think that looks good, and this is the answer that we got. Come on. Okay, that's fine. All right. Hello, hello. 1500 t to the 5th divided by 3t squared plus 2 to the power of 4. And we don't need this extra page. Delete the page. Let's see, 1500 t to the fifth. This looks good. Okay, I think we got all of these. And then E, yeah, we did that one as well. Okay. So again, since this is a pre-recorded video, keep in mind you can pause it. Even if you're live, you can still pause it. With a good idea, when you get a copy of the original, pause it and work it yourself and see if you can get this as a solution on your own and then compare at the end. Okay? Let me see. Calculate the derivatives at a point. Let h be this. Use the values in table 3.3 to calculate h prime of 1 and h prime of 2. Oh, okay. So let's write down what we have. So for example 3, we have h of x equals f of g of x, all right? So then they want us, and we're also given this table 3.3 that says that when x is 1, f prime of x is 5, g of x is 2, and g prime of x is 3. All right, we have this table. Okay. Then this example asks us to calculate h prime of 1 and h prime of 2. Okay. So if we're going to do h prime of 1, that's going to be I want to write it that way. Let me think about it. I'm just trying to think of how to write it. Here, let me do this. Let me do the following. So I'm going to do this. I'm going to say let u be g of x. All right. So then if u is going to be g of x, then when we do h prime of 1, that's going to be the derivative of f with respect to u times the derivative of u with respect to x. I think that's how that goes. And we don't really write df, it's usually f prime. Let me see their notation. That's why I'm pausing. I'm just thinking of proper notation. Yeah, I didn't want to write it that way. Anyway, okay. So what's f prime of 1? Do we have... Okay, when x is 1. So when x is 1, I feel like I'm still not doing something right. Five, and then g prime is 3, so 15. It just looks weird to me because it's not right. Oh, f prime of g of 1. Okay, there it is. So then f prime of g of 1, well, what's g of 1 is 2. Oh, okay, maybe I should write it that way. I don't know why they're doing it like that, but it's fine. Let's back up. Let's do it this way. So we're going to say h prime of 1 is going to be, okay, so the derivative of the outside function is going to be f prime of g of 1 times the derivative of the inside function is going to be g prime of 1, okay? That's why I was pausing. I was trying to think about the proper way to write it so that we could see it. But it's essentially just a chain rule. The derivative of the outside function times the derivative of the inside function. Okay, so I think we're okay now. So then if we're going to do, this is going to be, now what's g of 1? G of 1 is 2, right? So that's going to be f prime of 2 times g prime of 1. Do we, no. Well, we don't know f prime of 2. G prime of 1 is 3. Oh, you know what? I think the table is cut off. Let me go like this. Let me go to crop. It is cut off. I was like, something is missing. Okay, it's right here. Boom. I was like, what is going on? Okay. All right, I think we're back in business now. Come on. Okay. All right, that's what we needed. So the other part of the table, oh no. Yeah, I'm sitting up here like, what is going on? So the other part of the table that we were missing is that when x is 2, f prime is 7, g is 1, and g prime is 4. Okay. I was like, what? Okay, so now f prime of 2 is going to be 7. So this is going to be 7 times g prime of 1 is 3. Should be 21. Let's see, how do we do? We finally made our way. Again, that one was weird. Like, they were just trying to change the notation some, but it's fine. So let's see, how do we do? Example 3. Okay, so 21 was good. So we need to go back and do h prime of 2. Okay. So let's do h prime of 2, right? So this is going to be f prime of g of 2 times g prime of 2. So the derivative of the outside function times the derivative of the inside function. So what's g of 2? So when x is 2, g is 1. So that's going to be f prime of 1 times g prime of 2. What's f prime of 1 is 5. G prime of 2 is 4. 5 times 4 is 20. Okay, we finally found our way. That was an adventure. Style, okay. So I think 20 is good. And do we need all that space? I could shrink this down to 1 page. Let's shrink it. Okay, that'll be fine. Okay. So let me get rid of this page. 20, we got 21 and 20. Okay, those are good. Okay, so we got to the bottom of that. So this example 4, applying the chain rule, says a trail runner programs her GPS unit to record her altitude in feet every 10 minutes during a training run in the mountains. The resulting data are shown in table 3.4. Meanwhile, at a nearby weather station, a weather probe records the atmospheric pressure at various altitudes shown in the table. Use the chain rule to estimate the rate of change in pressure per unit time experienced by the trail runner when she is 50 minutes into her run. So we seek the rate of change of the pressure with respect to time, which is given by the chain rule. It says, use the chain, estimate the rate of change in pressure per unit time. So we can talk about the pressure in regards to the altitude and then the altitude in regards to time. Okay. So we want us to find the rate of change. Why does it look like that? We're asked to find the rate of change of the pressure with respect to time, but we can do this by finding the rate of change of the pressure with respect to the altitude times the rate of change of the altitude with respect to time, and this will allow us to finish where we need to finish. When the time is 50 minutes. Okay, let me add a page. Okay. So the altitude, let me see, at 50 minutes, the altitude, okay, rate of change. So we might have to use the slope formula, right? So if it's been 50 minutes, so we can do that in regards to the original. So let me see, at 50 minutes, I'm trying to think. I'm just trying to make sure I'm doing this right. Let me just kind of glance at it for a little bit. Here, yeah, I think that's what we need to do, right? Let me think about this one. So at 50 minutes, right? I'm still just going to use the original. I'm going to do my y2 minus y1 over x2 minus x1. So if we're doing altitude at 50 minutes, so my altitude, so I'm going to do this 12,330 minus 10,000 over, and I'm kind of doing this off the cuff. This might not work. If it doesn't, we'll go back and fix it. So that's the rate of change of the altitude with respect to time at 50 minutes. And then so at 50 minutes, if she's at 12,330, so then we want the rate of change of the pressure with respect to the altitude. So the pressure goes from 12,330, so that's 793. So we're going to say 793 minus 1,000 over the 12,330 minus 5485. Okay, let me just continue with this train of thought and see what happens. So since it was rate of change, I did my rate of change from the original to that point. Let me see, can I cancel anything? No. So let's crunch these numbers. That first one, if that were 800, that would be what, 207? Negative 207? I'm just gonna use the calculator. I'm trying to do these by hand. Not that one. Nope. Okay, that looks good. Let's reload and refresh. Okay, that looks good. So I'm gonna load the calculator here. I'm gonna just crunch that number. I just want to see, and then if we get it wrong, we'll come back and fix it. So the top is 793 minus, nope, 793 minus 1,000 divided by, notice my use of parentheses, 12,330 minus 5485. 5485. We're going to say times, we got this 12,330 minus 10,000, 1, 2, 3, divided by 50. Okay. I think we're okay with that parentheses. Let's see, rate of change of the pressure with respect to time. So the average, it looks like it decreased by 1.41. What's the units for pressure? Hectopascals. So it looks like the pressure decreased. So we're going to say minus 1 point, and we're going to say approximately 1.41 hectopascals, HPA. Okay, let's see how do we do. So with our train of thought, this is the result that we get. We're going to go style like this. Okay, let's compare that to their result. Doggone it. Every time I finish these, I don't be needing all the extra paper I think I'm going to need. I'm just going to fit this on the page, then we can move forward. Okay, let's see how do we do. First, I'm gonna get rid of this extra page for right now. Delete. 1.41 hectopascals. Oh, okay, let me think about it. 1.06. Let's see if we can go back and figure out what did we do. What are we missing? 765. Maybe we just read the chart wrong. I think I probably just read the chart wrong. 793, right? Pressure 7. I did it based on the original, but it looks like they didn't do it based on the original. They did it based on, we seek the change. The runner is this in 50 meters, so we must compute this at 50 meters. These derivatives can be approximated by this. I see. Okay, let's go back and try their technique. Okay, so I just kind of assumed that it was the original. Let's see, the 1,000. It looks okay. Okay. So let me see. 50 minutes. The change. I gotta think about this one. Give me a moment. So the derivative of the pressure with respect, so then we're going to use f of x plus the change. So at 50 minutes, oh, the change is 10. Maybe it's 10? Let me think about it. That's not right either. Let me see. The pressure with respect to the altitude is 50. 1 times 50. These derivatives can be approximated. A is the 12,330. My question is, where's the 1,000 coming from? Like, why are they choosing 1,050? That changes by 10. Is that changing by, and that's not changing by 1,000. Okay, so I just got this one wrong. I'm trying to think about it. The rate of change, I don't see why, I still can't see why mine isn't working. Pressure, was this one this? Minus that, over that, minus that. That didn't work. Did I type it in wrong? 793 minus 1,000, 12,330, 5485 times that minus 10,000 divided by 50. 50 minutes, 12,330 is here. Unless they just use the previous. Only thing I'm not sure on is the 1,000. So in the derivative formula, it's usually f of a plus some change. So the change is 1,000. Only thing I could think is that it's coming from here. But I didn't want to assume. There's something that I'm missing there, and I'm not seeing it. I'm gonna have to scrap this one. I mean, the idea is there. It's just I'm just trying to get to the nitty gritty, and I'm doing it on the fly. I feel like everything else is fine. Let me see, 60. Oh, okay. Rate of change. So they used the one to the right. So I just used the wrong points. But yeah, and that's why it's an approximation. Okay, I can see it now. So then here, the 1230, which is this one, plus the change. So there's where the 1,000 is coming from right here. So they said this one plus the next one. So they found the difference, the rate of change from here to the next one. So basically, it's the 765 minus the 793 over this minus this. So we had the right idea. We just chose the wrong points, right? That's what it was. I was like, that should work. And then right here, if it was at 50 minutes, they did the 60 and the 50. So so basically this is this one minus this one over this minus this. Now we're there. Okay. So again, we chose our pointed question in regards to the original. They chose the pointed question with the next point to the right, which makes sense because we typically want as that point gets closer and closer to ours. So keep in mind these are approximations and they are influenced by your point of reference. But let's go back and at least we can actually what we did was fine. We just had to choose different points. So I'm going to just strike through this for right now. Like so we weren't wrong. We weren't that far off. That's why I kept sitting with it. I'm like something's a little. It's just we should have chosen a couple of different points. So what I'm going to do is strike through this. It's not all the way wrong, but the idea was there. But that's why I'm leaving it. I'm going to leave it there. But I'm going to go ahead and match what they're doing and show how our logic was fine. The only change we need to make was choose a different set of points. So if we're concerned, so again, let's kind of back up and give this a go again. So if we're doing the change of the pressure with respect to time, we can say the pressure with respect to the altitude times the derivative of altitude with respect to time, and that'll give us finish us where we need to be. So if we want to do at 50 minutes, right? So then we had to use the second point because we were doing this in the original. We should do this in the next, right? So we can still do y2 minus y1, the pressure, right? So 50 minutes we're at 12,330. So that means we need to do these two guys here. So we're going to do the 13,330. This is going to be 13,330 minus the 12,330 over 765 minus 793. 765 minus 793. That's not a 3. So that's the first rate of change. The second one, the change in the altitude with respect to time. So we're going to say the 60 altitude is 12,710. 12,710 minus 12,330 over 60 minus 50. Okay, so sorry about that presentation. It's like that sometimes, you know, you just have to, but I could see it. I was like I know I'm looking at this proper, but again, the error came because we chose different points of reference. I chose the 50 and the original point, where they chose 2 points that were closer to each other because what we're trying to do is approximate the slope of the tangent line. So you want points that are closer when possible. So let's crunch these numbers. I mean, we know this will work, but I just want to go ahead and do it since we're here. So then the first one, we're going to say the 13,330. 13,330 minus 12,330 divided by 765 minus 793. That closes off the first term. We're going to say times 12,710 minus 12, 330, 30. I need another set of parentheses here. I'm going to insert a parenthesis. This will close off the top there, and then we're going to basically say divided by 10. Okay. And so now we should get our desired result of negative 1.06. Let's cross our fingers. 12, 7, 10, 12, 3, 30. 60 minus 50 is 10. 13, 330, 12, 330, 765 minus 793. Oh, there it is. Nope. Let me go back and look at my numbers. The pressure with respect to the altitude, right? Oh, did I get that reversed? Oh, I see it. I did x over y instead of y over x. Ugh, I am chock full of mistakes this morning. So this needs to go to the bottom, and this needs to go to the top. All right, I think we are just about there. Let's try this one more time. Let me make sure I did the other one right. The pressure needs to be on top. I think I got that one. This is the altitude with respect to time. Altitude needs to be on top. Okay, I think that was fine. Okay, let's try this one more time. Okay. So now the first one is 765 minus 793 divided by 13,330 minus 12,330. Okay. That's the first one. Then we're going to say times. We got 12, 7, 10. Nope. And I need another set of parentheses here. Insert. 12, 7, 10 minus 12, 3, 30. Then we're going to say divided by 10. Close that off. Okay. Man, that was an adventure. Now we finally got it. Negative, come on. Ouch. 1.06 approximately. HPA. So again, I left the error there just because I think it's a good learning experience. I just want you to realize that, like, you know, those things happen. And you just have to do the best you can and just keep it moving. Style, let's go here, here. Okay. Let's try another one. I know we kind of stumbled through that one, but that's just how it came out. That's fine. I'm not gonna worry about that. Okay. So we weren't far off, but we did learn something there that we needed to talk about. So, all right, let's try another one. Chain rule for powers. Yeah, this is essentially what we were doing. Okay, let's do this one. So we're almost there. So let's go example 5. We're asked to find d by dx. Let's see, we got tan of x plus 10 to the power of 21. Okay. So this should be the derivative of the outside function, which is going to be 21. The inside stays the same, tan of x plus 10. That becomes a 20. And then we're going to say times the derivative of the inside function. Tag on it. Tan, I don't remember tan. So I usually use like the quotient rule. So derivative of tan, sine over cosine. So the bottom, which is going to be cosine, times the derivative of the top. Derivative of the sine is cosine, so it's going to be cosine squared. The bottom is the derivative of the top minus the top, which is sine, times the derivative of the bottom, which is cosine. Derivative of cosine is negative sine. So that looks like it becomes like this, over cosine squared. Okay. So reciprocal of cosine, that's going to be 1 over cosine, which is secant squared, all right? So this becomes 21 times the tan, let's do it like this. 21 secant squared times the tan of 10 to the power of 20. Okay. Style like this. Okay. So for example 5, 21 tan x plus 10 to the power of 20 times secant squared x. Okay, cool beans. Okay. Composition of three functions. Calculate the derivative of sine of e of to the power of cosine. Okay. So it's just outside times the derivative of the inside, and then the second outside times the derivative of the inside. So we just have to do it multiple times in succession. We don't need this anymore right now. Okay. So then for example 6, ouch, let's add a page. Well, let's just hold off. We might not need it. So we're asked to find d by dx of sine of e to the cosine of x. Okay. So the derivative of the outside derivative of sine is cosine of that thing, e to the cosine of x. The derivative of e is itself. There's going to be e cosine x. And then the derivative of the inside function there, derivative of cosine is negative sine of x. Okay. So then I'm going to write the answer in the following way. Negative e cosine x times the sine of x times the cosine of e to the cosine of x. Okay, so does anything simplify? Okay, we got a double e cosine. So we add those exponents, so that's going to be a 2. No, that's not an e cosine. Yeah, I'm going to leave it. I got this answer. Okay. Let's see how do we do for example 6. Negative sine x, e to the cosine x, cosine of e to the cosine x. Cool beans. Yeah, that's as far as we can take that. I think this is the last one. All right. What a day, what a day. That was fun. We had a little bit of adventure. We got lost for a little bit, but you know, the best way to kind of to learn a location or find things is to get lost. Whether it's life or actual navigating or I guess apparently mathematics now, the best way to kind of find the solution or find yourself or find your way is to get lost. Okay. So I definitely was lost for a moment, but then we found our way. Okay. Let's look at this one. Combining rules, find the derivative of this function. Okay. So for example 7, we're asked to find d by dx of, we got x squared, square root of x squared plus 1, like this. And we want the derivative of all of that. Okay. So this is for, so we have the product rule first. So it's the product rule is going to be the first thing times the derivative of the second. So if it's square root, that's to the power of a half. So that half comes down. It's going to be x squared plus 1, and it's going to become to a negative 1/2. And then, so we got to use the chain rule there. Times the derivative of the inside function is going to be 2x. Okay. So that's the first times the derivative of the second, plus the second times the derivative of the first. So that's going to be a 2x times the square root of x plus 1. Okay. Let's see. So this cancels this. We're going to get an x cubed there. We could get a common denominator. Let's keep going. Let's get a common denominator and see if anything cancels. So then we're going to have, we got the square root of x squared plus 1 under x cubed plus 2x times the square root of x squared plus 1. Okay. So if we multiply the top and the bottom, if we multiply this by 1 in the form of root x squared plus 1 over root x squared plus 1, all right, we can get a common denominator. Okay. So then we're going to have x cubed plus, there's going to be 2x. Now, those is going to be that thing squared. So the radical essentially is going to be gone. We're going to say x squared plus 1, like that. I think this is okay. Divided by, we're left with square root of x squared plus 1. Let's see if we get anything to cancel. I'm going to just go ahead and expand it all the way out. So we get x cubed, that's going to become a 2x cubed plus 2x over this. Okay. 3x cubed. Does anything cancel? 3x cubed plus 2x over x squared plus 1. I can't see anything cancel. We could factor out an x. That'll leave us with 3x squared plus 2. So I'm gonna stop here for this one. I think this is for, I can't see anything canceling or can't get anything to work out. So I'm gonna let that be style. Let's see, how do we do? This was 7, right? 3x cubed plus 2x square root of x squared plus 1. Okay. All right. Like I said, that was an adventure, you know. Again, I'm a multi-dimensional being having a human experience like everybody else. What that means is that I make mistakes too. I'm not, you know, making mistakes is our birthright as humans, right? So we're allowed to make mistakes and it's okay. Ooh. We just want to minimize those as best we can and just do our best, right? Okay. So with that, again, the major announcements for this week. Exam 2 is available on Pearson. We get unlimited attempts until this Saturday. So I went on intentionally and loaded it a little bit early because I wanted to give you a little bit more time than like about 24 hours for it. I just wanted you to get it in. You get the unlimited attempts. You get whatever score you want. And I'm kind of being lenient because, you know, we were kind of forced into online and, you know, we didn't really sign up to be online. So hopefully you could take advantage of this. You know, so again, you can get whatever score you want. Past the deadline, there's going to be a late penalty. But again, the main things that we're looking for right now, go ahead and get this exam 2 on Pearson submitted. And there's a participation and honesty quiz on Moodle that we need to submit. Otherwise, I can't give grades. I can't give official grades until that quiz has been submitted. Okay. All right. On that note, we're actually going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Peace.